Up until today, all we've worked on is simplifying rational expressions and doing all operations with rational expressions, right? Your quiz was adding, subtracting, multiplying, dividing, and solving rational equations. Now we're going to focus on the graphs of rational functions. And there's a lot that goes into these graphs. We get a lot of different features that don't show up in, like, say, a polynomial graph or a quadratic graph. So the whole graphing process is going to take us this whole week and maybe even into a little bit of next week. This is the last thing that we're doing in this unit. So even if, like with the quizzes, I'll pass those back to you all tomorrow. We'll take a look at all the expressions and the equation stuff. As always, there will be some way to get points back. I'm still kind of thinking about how I want that to look like. There might be more than one opportunity or more than one way to kind of get those points back from that quiz. Okay. So today's our first day of jumping into some of the features behind graphing rational functions. We're not going to graph them today. All we're going to try to do is identify these features. Any graph that we look at, I'm going to actually pull up on Desmos because it really helps us kind of get an idea about these different features. So up at the top here are kind of all the things we're focusing on just today. Tomorrow we'll look at a different feature, but today we're looking at what's called a vertical asymptote, and then also a hole that shows up in some, rational functions. So first off, a vertical asymptote, and both of these. So vertical asymptotes and holes occur because of discontinuities in the domain. If you think back to the quiz, right, I had you all identify the domain restrictions. So wherever we divide by 0, that's a problem, and that creates these features on the graph. So like I said, this is a fancy way of saying that they happen whenever we divide by 0. So we still want to focus on what makes us divide by 0, where are those domain restrictions at. That's why I kept pushing that on every assignment and when you all were taking the quiz. Then depending on what kind of happens when we divide by 0, we either get a vertical asymptote or a hole. A vertical asymptote, which I'm going to abbreviate VA, this is just describing it. It's a line that goes through, or it's a line on the graph that we approach. I think I have some typos there. It's a line that our graph approaches, but we never actually touch it. We get infinitely close to that line, but we never 100% get there. And that's a really important piece for us to think about. And again, it happens because of the discontinuity in the domain. I'm going to show you what that looks like on the graph here in just a second. The next feature, and this one's a little bit more confusing, and a lot of students will be like, well, a hole. Like, what is a hole? It's exactly what you would picture. It's a hole in our graph. It's a full-on, like, gap. Now, that gap is actually, like, infinitely small. So a lot of times, we won't even see what that hole looks like. Okay, we have to kind of zoom in or add it into our graphs to be able to see it. But that's still discontinuity. It still exists. The hole works as a point. There's an x and the y coordinate to the hole. So when we go to find the hole, we're going to have to find not only the x coordinate, but also the y coordinate. And that gets a little complex there. Last thing is how we find these things. So to find vertical asymptotes and holes, we factor both numerator and denominator, just like what we've been doing. If the factors divide out, right, a lot of simplifying expressions has us taking like an x plus 3 dividing by x plus 3 and dividing those out. If the terms divide out, then we have a hole at the location at that x value. And that's the value that makes the factor equal to 0. If instead we factor and we find a value that we divide by 0, but that term doesn't divide out, that's where we'll get the vertical asymptotes. Okay, and again, all this will make sense as we go through some examples. So yeah, let's go ahead and kind of take a look at this right now. So this is where I'm going to pull up Desmos, but before we even do that, I want us to factor this equation. And again, with rational functions, it's important that we factor every single piece, including GCFs. So f of x, our numerator, I can factor out at 2. And I get x minus 4 as the other factor. In the denominator, I'm thinking of two numbers that add to negative 3 and multiply to negative 4. That would be negative 4 and positive 1. So this factors to x plus 1 and x minus 4. Now, before we start dividing things out, and this is something that a lot of you made some mistakes with on the quiz, we need to identify the discontinuities in the domain right now, okay, not after we simplify. So our discontinuities are going to come from this x plus 1 and me setting that equal to 0, and this x minus 4 and setting that equal to 0. So I get x equals negative 1 and x equals 4. Now again, as a whole, these are the discontinuities in the domain. So at negative 1 and at 4, we are either going to have a vertical asymptote or a hole. We're not sure what yet. So negative 1 and 4. So now that we've factored and identified the restrictions in our domain, now we're going to try to identify at negative 1 and at 4, do we have a hole or a vertical asymptote? Part of us figuring that out is what factors divide out. Well, those x plus 4s, or excuse me, those x minus 4s, they divide out and they go away. So I get 2 divided by x plus 1. This is the most simplified expression or equation of the original function. Now, with this function, it's still, and I'm going to graph these both in a second on Desmos. These are the exact same. When I just graph the simplified function, we're not going to have that same value of 4 because those factors divided out. But again, everything we do always goes back to the original function here. Okay, so now, because the x minus 4 is divided out, that means that at x equals 4, we have a hole. Okay, and that's what I meant above. If you read of how we get the holes, if the factors divide out, then we have a hole at that location. X minus 4 is divided out, so we have a hole at the location that makes that term equal 0. Then whatever factors survive all the canceling out or all the dividing out, okay, whatever factors survive, we're going to have vertical asymptotes there. So the only term that survived in our denominator, survived all that canceling out, is x plus 1. So that means that x equals negative 1, there is a vertical asymptote. And we are going to have to do one more thing with this hole, but this is where I'm going to pause and show Desmos. So for anybody that's watching the video, I'm going to have you go to Desmos and type this in to Y1 and then this in to Y2. I'm going to pause the video while I do that. Actually, I'll still do it. Okay, so our first function is 2x minus 8 divided by x squared minus 3x minus 4. And then our simplified function we say is 2 divided by x plus 1. Okay, so the first thing I want to point out, you'll notice that we're only seeing one line here or one graph here. That's because these are the exact same expressions. They're the exact same, I shouldn't say equations, but they're the same expressions, right? The blue is what we simplified the original function to be. Now, what happens here is you can see this kind of split in the graph, okay, right in the middle. Well, that split in the graph, that's that vertical asymptote that we said was at x equals negative 1. And so this green line, that's not really part of the graph, but that's what our graph is going to approach, and it gets really, really close to it, but never actually touches it. And you can see that with the red, which is our original function, and the green, the vertical asymptote. So we just keep getting closer and closer and closer, but it's by very small amounts. Okay, so that's that vertical asymptote that our graph approaches, but never actually touches that line. Now, the weird thing is the hole, because right now when you look up there, you're like, hey, there's no hole anywhere on that graph, and you are correct. Okay, but that hole we said is at x equals 4. Well, when I go to x is 4, if I try to put a point there, it'll tell me that's undefined. And you can see that when I get to that point, I have to zoom in a little bit, the graph will legit have an open space in there. And that's what, when we eventually graph all these functions, you're going to put an open circle like that, representing that the hole exists there. Okay, so that's what I mean by the hole is a point on the line. Okay, that's still a part of our graph. It's just that we skip over that point. Now, the reason why we don't see it is because if I plug in x equals 3.999999, and you can list out as many nines as you want, we still have a point there. So this hole is actually considered to be infinitely small. Okay, it's so small that even if I zoom in on the point at exactly 4, it will never show up on here. Okay, and you can look at the scaling. I'm at 4.001 and 3.999, and that hole still does not show up on the graph, but it still exists there. Okay, so last thing I want to point out is we're really graphing the original function. It is the same function as what we simplified to in the blue. The only difference is the blue function, which is what we simplified this to be, there's no hole there because those factors divided out and it's simplified. Okay, so what the blue can be helpful for is to have us find the y coordinate of that hole, which is at 0.4. And we're going to talk about how we can figure that out without looking at the graph. Okay. All right. So like I said, we were almost done. We've identified the vertical asymptote. We've identified the hole. But the hole, there is going to be an x and a y coordinate. To find the y coordinate, so to find plug x equals 4 into the simplified equation. Sorry, that says simplified equation. And the reason why that works is because when I plug in 4 to that simplified equation, I'm not going to get that error in the domain. I can plug in 4 after we take out those common factors. So this will tell me that exact y coordinate of that location. So I'm going to take x equals 4. I'm going to plug it in for this x right here. So f of 4 equals 2 divided by 4 plus 1, which is 2 divided by 5, which is 0.4. So there's a hole at x equals 4, but the exact location of it is 4 comma 0.4. All right, and again, the reason we had to plug it into that simplified equation is if you plug it into the original, you're going to get an error because you're dividing by 0. Okay, let's go through a few more examples. Hopefully, right now we can talk through that by going through another few examples. And even better would be if we had some questions after doing this last few examples here. All right, so we're going to take all 3 of these equations, and we're going to work on identifying the vertical asymptotes and the holes, okay, of all these functions, regardless of how we start. And this is almost the same for anything we do with something that is rational. We need to factor the numerators and denominators. So I'm going to start with that. Part A, the numerator does not factor. It's just an x. The denominator of x squared minus 9, that factors to x minus 3 and x plus 3. So the discontinuities in our domain, or we'll call them domain restrictions, the domain restrictions are that x cannot equal 3 and that x cannot equal negative 3. Sorry, that's a negative. It kind of blends in with the equal sign there. So 3 and negative 3 are domain restrictions. And we're going to get either a vertical asymptote or a hole at each one of those restrictions. Because there are no factors that divide out, I would say that everything survives the canceling. And so that means that each of these values are going to be vertical asymptotes. So vertical asymptotes are at x equals 3 and x equals negative 3. And then here, holes, there are none. Okay, because no factors divided out. For us to have a hole, those factors need to completely divide out. All right, let's move on to part B. So g of x. Again, the first thing I'm going to do is factor everything. The numerator of x plus 3 is as factors as it can get. The denominator of x squared minus 9, same factoring as before. So that factors to x plus 9 and x minus 9. Let's try that again. How about x minus 3 and x plus 3? This time, and let's actually state the domain restrictions. I'm going to abbreviate that dr. Once again, x cannot equal negative 3 and x cannot equal 3. So we have the same domain restrictions. But this time, we get these x plus 3's to divide out. And so our simplified equation of g of x is 1 over x minus 3. And they divide out because anything divided by itself is 1. So really, we are graphing the simplified equation. We're graphing the simplified equation, but now we have a hole that doesn't show up in this equation, but it does show up in the original function. So first, the vertical asymptotes. What survived the canceling with the x minus 3? What makes that 0 is positive 3. So we have a vertical asymptote at x equals 3, meaning we have a hole at the other discontinuity, which is at x equals negative 3. Now, as of now, sorry, that should say x equals negative 3. As of now, we don't know the exact location of this. We just know that it happens where x is negative 3. To find the y coordinate, I'm going to plug that right back into the original function, or this simplified function. So g of negative 3 equals 1 over negative 3 minus 3, which is 1 over negative 9. And so that hole is at negative 3, comma negative 1/9. Yeah. What'd I do? My goodness. Negative 1/6. Thank you, Lucas. Math is hard. All right, and then part C, and this is where hopefully we have some questions after this. Again, trying to factor the numerator. Nothing I can do there. The denominator, for it to factor, I'm thinking of numbers that add to 0 multiplied to negative 9 or to positive 9. Those numbers exist. We can't get two numbers that multiply to a positive and add to a 0. One would need to be positive, one would need to be negative, and thus they'd multiply to a negative 9. Now here's another way that I can catch on to this. This denominator does not factor. Well, really what we're doing is we're taking the entire expression in our denominator and we're setting that equal to 0. Well, if I take this x squared plus 9 and I set that equal to 0 and try to solve it, just like we did in the quadratics unit, just like we did in the polynomials unit, I would subtract 9. And when I square root, I'm getting x equals plus or minus 3i. Well, an imaginary number doesn't show up on our graph. Okay, so for us to have any discontinuities, that would need to apply to real numbers. So because these aren't real numbers, that means that we can plug in any number for the denominator. And so there are no discontinuities or no domain restrictions, and thus no vertical asymptotes and no holes. So domain restrictions, none, which means that our vertical asymptotes, there are none, and then the holes are also none. Okay, so this graph would be considered continuous because there are no breaks in that graph there. Okay. What questions might we have about identifying vertical asymptotes and or holes? Again, don't be afraid to ask. Okay. Well, what I'm going to have us do is do the exact same thing for the next three functions. Can you identify, if any exist, holes and vertical asymptotes of each? Do your very best with that. Ideally, work with the people in your group. Start with the factoring. Make sure you all factor correctly. Number one already has kind of a weird factoring. So work together to factor and find these points. We'll go over them in about 10 minutes. All right, so before we go over everything here, first off, this is not easy. Okay, we're at the point now where you will not hear me say that anything we do moving forward is easy, which is why it's so important that we are doing math the right way. For example, when I give you time to work on problems, you're working on problems. Okay, walking around look like we did that. Doing homework on a regular basis. At this point, it matters. And if you're not doing the homework on a regular basis, don't expect assessments to go well. Okay, there's too much going on for you to just study in one night and think the test is going to be really easy. Okay, you need to be doing math on a regular basis. Now, by regular basis, I'm saying like maybe 20 minutes outside of class every day goes a really long ways. Okay, if you eat lunch during your lunch period and then spend 20 minutes doing math, oh my gosh, you'd make math so much easier on yourselves. Okay, but these things need to start happening if we're wanting to improve how we're doing in this class. Now, again, before we start, really what we're doing here is we're factoring everything. So factoring is a huge part of this, and that's why I've pushed factoring for so long now. And then we're just taking each factor in the denominator and setting it equal to 0. That's what I would hope we can all get to. After that, the vertical asymptotes and holes, that's going to take practice. Okay, so let's look at all these here. So number one, this is me just factoring. So the numerator factors the x minus 4, x minus 1. The denominator, I notice there's a GCF of 2. So I'm going to take that 2 out, and then I have this x squared minus 1. We need to recognize that that might factor. And it factors by me finding numbers that add to 0 and multiply to negative 1. That'd be positive 1 and negative 1. So that denominator factors the x plus 1 and x minus 1. Now, before I cancel anything out, I think it's really helpful to write down the domain restrictions before I simplify anything. And right now, my domain restrictions come from negative 1. That comes from the x plus 1. If I plug in negative 1 there, that's 0. So that means I have something going on in negative 1. X minus 1. That means there's a domain restriction at positive 1. So I would always write down where we have domain restrictions at. And then just know that each of these values should either show up as a vertical asymptote or a hole. So identifying the domain restrictions happens before I simplify. Then I recognize that the x minus 1s divide out. I divide them out, and this gives me my simplified equation. So anything else I do moving forward is with this simplified equation. Because the x plus 1 survived all the canceling, that tells me that the domain restriction of -1 is a vertical asymptote, which tells me at 1, that's where the x minus 1 is divided out, and 1 makes that 0. There's a hole there. So I know there's a hole at x equals 1, but I don't know the y coordinate yet. To find the y coordinate, I am plugging 1 right back into the original, or into the simplified equation. So 1 minus 4 divided by 2 times 1 plus 1, which is -3/4. So that hole is at 1 comma -3/4. Any questions there before we move on to number 2? Again, the factoring really, really important here. All right, number 2. Okay, so the denominator, I take out a GCF of 2, and that makes that x squared minus 4. The x squared minus 4 does factor. It factors the x plus 2 and x minus 2. That means I have domain restrictions at +2 and -2. And again, I think it's really helpful just to state those domain restrictions before classifying them as a vertical asymptote or a hole. Well, since the numerator is 1, nothing's going to divide out. And so that means at those 2 locations of our domain restrictions, they are just vertical asymptotes. So I have a vertical asymptote where x is 2 and where x is -2. There are no holes there. Questions on 2? I did. Yep. So I factored the x squared minus 4 to get x plus 2 and x minus 2. And then setting each of those equal to 0. Remember that GCF of 2 does not change the domain restrictions. It needs to be a variable for us to get a restriction in it. So that GCF of 2 does nothing in terms of identifying domain restrictions here. All right, and then the last one. So a little bit more work on the factoring here. Numerator factors to x minus 4, x minus 3. You will always hear me encourage you to take out a GCF to make the a value positive. So instead of taking out a GCF of +2, I'm taking out a GCF that is -2. And that makes my a value 1. When a is +1, the factoring is a lot easier, right? I just need to think of 2 numbers that add to b and multiply to c. Those numbers are -4 and +1. So this is everything completely factored out. X minus 4, x minus 3, and then -2, x minus 4, x plus 1. My restrictions come from what makes each factor equal to 0. So x minus 4 tells me that x cannot equal 4. X plus 1 tells me that x cannot equal -1. Then those x minus 4s divide out, giving me my simplified equation of x minus 3 divided by -2 times x plus 1. Since the x plus 1 survived all the canceling, that means there's a vertical asymptote at -1. But the x minus 4s that we canceled and divided out, we've got a hole at that location. So there's a hole where x is 4. The y coordinate, after plugging that in, is 1 over -10, or -0.1 if you converted it to a decimal. Converting it to a decimal does make it a lot easier to graph it. So your hole is at 4, -0.1. Okay, well that is it for today.